Good morning, dear friends, dear RAAD community members, dear colleagues and friends. We are very happy to welcome you in Serbia, in Belgrade, in this beautiful building of the Palace of Science for the 34th edition of International Conference on Robotics in Alpe-Adria-Danube region, RAAD 2025. I have a pleasure to say a few words on behalf of conference chairs this year, on behalf of three organizing institutions: University of Belgrade School of Electrical Engineering, Faculty of Technical Sciences, University of Novi Sad, and Institute Mihailo Pupin. But the organization of this conference was not only about these three organizations. In the organization, we've had huge support of all robotics community in Serbia, other academic institutions, our industry, and also, of course, members of International Steering Committee of RAAD. As a result of this effort, I think we achieved a great result. So this year we have 78 papers accepted and to be presented at the conference from 20 different countries. You can see the distribution of the countries on a slide. So, of course, majority of the papers came from a RAAD region, from Serbia, Slovenia, Germany, Italy, Croatia, Czech Republic, France. But we are also very happy to see papers and authors from other countries outside the RAAD region, from Denmark, from the Netherlands, from Spain, Turkey, Russia, even Emirates. So one can see that year by year, RAAD enlarges its footprints and establishes as the largest European conference on robotics. I remember a discussion about the position of robotics today, the discussion that we had last year in Romania, and the final conclusion that that I'm using a lot also for my lectures at university, and that's that what computers and software were in 90s, robotics and artificial intelligence are today. And I think that this is the message and this is the vision that we should all have in mind, and to really act accordingly to prepare our regions for the time that is coming. And on the slide you can see a word cloud of all of keywords of the papers of RAAD 2025, and I'm sure that all of you can get inspired with some of the words and start discussion, and I'm really looking forward to discussion, and I hope that you will all enjoy it in the next 3 days. And to spark this discussion, we are incredibly proud to have a remarkable list of the keynote and plenary speakers for the RAAD 2025. So I'm sure that we are all very looking forward to their talks, and even more than that, to spending time with them and sharing the ideas and listening to their feedback. And I really invite young researchers and PhD students to use this exceptional opportunity to talk to Arash, to Zoran, to Alin, to Strahinja and Katja. And I would like to use this opportunity to give them big applause on behalf of the RAAD community. Since all and RAAD community and our academic community is about the sharing the knowledge, so this year we go a step further and we organize broadcasting for all plenary talks via YouTube channel of the Palace of Science. So I hope that many others around the globe will enjoy the talks of our plenary speakers. Since the conference is, of course, it's not only about the knowledge sharing, the RAAD is also about meeting the region, enjoying the region. There is just a short video teaser to announce city tour tomorrow, and then you will have opportunity to meet Belgrade.
Upoznajte Beograd na mestu gde se sreću Beograđani. i na mestu gde se sreću stari Beograd sa modernim životom evropske prestonice.
Ja ovde dolazim od 1945. godine. Deda me dovodio, a ja sad dovodim svoje unuče.
A ovo je grad ispunjen istorijom i velikim pričama. Kao što je priča o počecima srpske države, o crkvi, priča o ocu i sinu.
Postoje ljudi koji svojim umom stvaraju misterije. Upoznajte najvećeg od njih. Upoznajte Nikolu Teslu i doživite njegovu genijalnost kroz izume koji i dan danas rade baš onako kako je on zamislio.
Ako volite baš stare priče, njih je ovaj grad prepun. Oko 7000 godina istorije na jednom mestu. Na vama je samo da istražujete.
I birajte. Šetnja boemskim ulicama pre ili posle večere. Uživajte u srpskoj kuhinji i uz dobru hranu može uvek da se dobro i zapeva.
Ili šetnja sa Beograđanima. Vi birate. Ali ćete se zaljubiti. Kao i ja. Dobrodošli u Beograd.
I hope that many of you will also fall in love with our beautiful city. And one of the symbols of the city is also our University of Belgrade as one of the largest and highest ranked university in this part of Europe. So it's my pleasure to invite Professor Nebojša Bojović, our Vice Rector for International Collaboration, to address the audience. Professor, please.
Ladies and gentlemen, esteemed colleagues, dear guests. It's my great honor to welcome you at the 34th International Conference on Robotics in the Albu-Adria-Danube region, here in Belgrade, hosted by University of Belgrade. The conference has long been a symbol of connection of minds, disciplines, and nations, united by the shared belief that future is something we build together. As someone whose academic journey began with the circuits and systems, and who spent decades teaching and learning at the Faculty of Traffic and Transport Engineering, I have always felt in a quite thrill in watching how theory transforms into practical, often astonishing innovation. In a sense, I was always a gadget person, but beyond the fascination with technology lies something even more meaningful, the belief that innovation must serve people, that robots are not just mechanical wonders, they are an extension of human intention, values, and dreams. The University of Belgrade stands at the crossroad today not only of geography, history, and collaboration, but also of transformation. We are not longer connected to be only a provider of excellent students. Of all, we are rightly proud of them. We are striving to become an active force in shaping the kind of innovation that makes the future more human, more sustainable, and more inclusive. A future where progress is not in a luxury, but something every citizen can feel in everyday life. It means in a smarter mobility, better health care, safer homes, and more dignity in aging. The path is not without the challenge. We are currently facing one of the most difficult chapters in the history of our institution, a period marked by financial hardship, halted operation, and a deep uncertainty about how long we can continue to function in such conditions. Financial pressures, logistical limitation, and structural uncertainty weigh heavily on our staff and students alike. And yet there is something profoundly meaningful about choosing to stay, to create, and to transform from within. In these moments that we are ground under our feet seems uncertain, the true excellence is for region. When we understand that resilience and solidarity are not just words, they are blueprints. And for those of us who remain, who choose to keep working, teaching, and building under the weight of real and growing uncertainty, knowing that we are not sought out of convenience, but out of deep love. Love for our profession, for our students, for our colleagues, and for the idea that the knowledge still matters even when the system around it are tested. To our international partners and guests, for your support, your recognition, and your collaboration mean more now than ever. In standing with us, you help strengthen the foundation of public education and research at the time we need courage, vision, and solidarity. Because in the end, all of us who remain, we do not do so because it's easy, but because we believe, and because we love the place too much to let it fall. Thank you, and let us continue building the kind of world all we want to live in. I wish you a great conference and great work in next days. You're welcome.
Thank you, Professor Boyd, for your great support and for your time dedicated to the conference. Although we are facing in university and academia significant challenges nowadays, also in Serbia as a society. So now I would also like to invite Professor Cvetanovic, President of the Council of School of Electrical Engineering, to say just a few words on behalf of the organizing institution. Miloš, please.
Thank you. Good morning, ladies and gentlemen. It is my great honor to be here today and to welcome you on behalf of School of Electrical Engineering and somehow on behalf of this endowment of Mildred Kostic, the building that you're currently in. Great pleasure to have that cooperation that help us to have more laboratories and perfect conditions for the research, and also to promote the science in Serbia and to wider auditory. University of Belgrade is one of the most significant academic institutions, not only in our country, but also in the region, with tradition of more than 200 years. And especially when it comes to robotics, there are legends, probably the names that you already heard of, like Miomir Vukobratovic or Rajko Tomic, and we have robotics developed. It is so horizontal that it is researched and developed in different institutions, not only our school, but also So beside the School of Electrical Engineering, we have mechanical engineering, we have different institutes and other universities. So it is a great honor to be part of it. And we are, especially at the School of Electrical Engineering, especially proud for our, let's say, young group of researchers dealing with the topic of robotics led by our colleague Kosta Ivanovic. I'm very thankful to him for promoting and helping to robotics have a great place in our school and very recognized place. Beside that, looking at the statistics, we all see that robotics gaining more and more momentum. And the projections for the next couple of years are astonishing. But when we look, and I saw somewhere that more than 4 million industrial robots are installed all over the world. And if we take a closer look, we see that majority of it, more than 70% is in Asia, while Europe is around 17% only. So besides all other challenges, I would say that for us as researchers, as academics, and as practitioners and engineers, one of the challenges before us is to help our local industry to embrace the robotics, to get it more and to invest in robotics and in the research. So that is something that we need to pay special attention to it. And besides everything that our Vice Director mentioned, I will just join them in telling that all the activities that you see around the city these days, you will see the students and the academic wider auditory that raise their voice for the rule of law and the freedom of speech. So I just want to raise your attention to it, and spreading the voice and the support from the wider scientific and academic community from the region, Europe, and the world will definitely help in our endeavors. So thank you for that. And I wish you a pleasant conference, fruitful discussion, and great time and pleasant time in Belgrade. So enjoy and have the nice one. Thank you.
Thank you, Professor Cvetanovic. Yeah, probably many of you from the region knows about great achievements of Serbian robotics in 60s, 70s, 80s. Professor Cvetanovic mentioned also a few of very important names in our robotics history, and I would like to highlight that the first hand prosthesis was built in Belgrade in 1963. Also first upper limb orthosis, famous zero moment point theory for keeping dynamic balance of walking machines. So it was very prosperous period of Serbian robotics in that period of time. After that came crisis, and then we needed some time to reintegrate in European research area, research space. One of the people who supported us most in this process in different capacities, from his ex-role as Secretary General of European Robotics Association to the latest activities and organizing session, this conference about the past of robotics in RAAD region and its influence to the future, is Dr. Uwe Haas. So I'm happy to invite Dr. Uwe Haas to say a few words.
Dear colleagues, dear friends, dear supporters of this conference, when the press is distributing the word, this is the year of the humanoid robots, then you wonder what's going on. Well, I usually respond, are you aware of the hard work, of the groundworks which were done in the RAAD community in what was earlier maybe Yugoslavia? Are you aware of what has been done in biology-inspired, mathematics-oriented, robotics 50 years ago, 60 years ago. And I usually add, this is scientific basis, verifiable and explainable, and based on biology and mathematics, not on 10 and thousands of millions data in a black box. I agree, history was not very kind to you, I agree. And I feel that this is to be solved, that we need to make sure the basis of your work should be made available to a maximum audience. I heard of these developments the first time in 2015. This is not so far away. In those days, I was responsible for managing EU Robotics, which is the European Robotics Association in Brussels, cooperating with the European Commission. And I had to organize a strategic meeting of the future of robotics in Europe. And looking for innovative ideas, I was advised to invite two persons, Professor Podkonjak and Professor Rodic, to this strategic meeting. And I managed to invite them, and they enriched the meeting a lot because they told us what the basic mathematical, biological, and physical works have been done in the past, and how there was a certain period of darkness, if you want. 2016 was my first RAAD, and I noticed that this period of darkness has disappeared. And this year's RAAD today is so impressive. It is really encouraging that this is thanks to the competence of all people working in this field here in the region, under conditions which are not comparable, or which were not comparable and still not comparable to many other European countries. Especially with Kosta Jovanovic and his team, under all these circumstances, developing now a situation which is completely different from the past. I'm convinced, you all agree, that this momentum of RAAD, this regional area, has grown. And I wish you all a successful conference, and I wish all of you to stay on. And in order to keep your energy going, there's a small lunchbox for you, Kosta, full of energy for you and your people, your colleagues, yeah?
Thank you.
It was my pleasure. Yeah. It's my pleasure.
Yeah. Excellent. Thank you. Yeah. So, yeah. Thank you for your kind words and for your constant support. We really appreciate. So, and when talking about the past and its influence to the future, and talking about the prosperity, I think there is no better place than this building, than the building of the Palace of Science, which was for almost a century, which was Adriatic Danube Bank, serving for the prosperity, economic prosperity of the region. And today we gather here and in this venue that now takes care of the prosperity, but in another terms, supporting science, research, and education as the biggest capital of the modern society. So I will just present a short teaser of the Palace of Science, and on the Friday you will have opportunity to have a short tour around the whole venue.
Ako postavljaš pitanja i tražiš odgovore, Veruješ u nepresušnu snagu ljudskog uma i želiš da znanjem menjaš svet. Ovo je mesto za tebe. Zakorači u susret inovacijama, gde granice nestaju, a sutra već počinje. Otkri neverovatna dostignuća nauke. Čuvaj radoznalost u sebi i svoju moć da saznaš i istražiš svet bezgraničnog. Palata nauke, zadužbina Miodraga Kostića.
So, yeah. So you see there is a lot of symbolic that we extend from Adriatic Danube now to our conference, which is Adriatic Danube plus Alps. So, yeah. So then I will leave the floor to Nemanja Đorđević, manager of the Palace of Science, to say a few words on behalf of the endowment of Miodrag Kostić.
So, dear colleagues and guests and all friends of robotics, it's really an honor to have you all today here. First of all, this is the biggest scientific conference that we ever made in 6 months long history of the Palace of Science. So that's something. And also we are proud to gather you here because there is a secret sauce of this Miodrag Kostić endowment. Here we combine not only scientific exhibitions and popular science, but we gather more than 19 different laboratories with real researchers. So we want to open to people not only to play with science, to understand some scientific phenomena, but to really see what is research today. And one of the really important laboratory that we have here at Palace of Science is certainly robotic laboratory. Also, a few of our colleagues mentioned the famous Belgrade's hand, and one of the copies of that hand you can also see at the second floor of this building, and we are also proud to have that here. I really wish you a great conference, interesting conversation, good flow, not only of conversation, but of coffee at the breaks. And we will be here with all of our science explainers and my colleagues to help you during these 3 days in any area that you think it will be interesting for you. And we also are open to learn things or two from you and to have the start of a conversation that will hopefully last at least for us for next 100 years. So at the end, once again, thank you for coming to Belgrade and to Palace of Science, and I hope you the best conference in the history of RAAD. Thank you.
Thank you, Nemanja. This was very encouraging. So I would like to express our biggest appreciation to our companies, sponsors that you can have here on a slide: Renex, ABB, Embrain, Bosch, Fanuc, Festo, Synapticon, Yandex, and KUKA. Without them, we could not enjoy, and we wouldn't enjoy this conference that much. Finally, there was a huge work, a huge effort behind the scenes organizing this conference, and please pay attention to those people, to Nikola, Zaviša, Maja, Veljko, Nikolina, Dragana, Branko, Filip, Nikola, Miloš, and Andrej. So I invite you to give them big applause. Thank you very much once again. It was really a pleasure working all together in organizing the conference. A few service info from my side, and I will finish with this. So on the ground floor, you will have an exhibition area with sponsor booths. So it's also a networking area, so you can also take your coffee, robot can serve your coffee there. Then we have on the 4th floor, we have conference rooms, so for the parallel sessions. And finally, on the 5th floor, we have a restaurant with rooftop. So I hope that you will enjoy the space. And also, we invite you all to scan this QR code to join the WhatsApp community, because we will use this WhatsApp community to share the latest announcement about the conference, its organization, and so on, which can be very important, especially during the evening sessions. So finally, it's kind of internal, but I would like to open this RAAD conference in a little bit different way, not just with hitting the gong or cutting the red tape, but it's a different way. So once again, welcome to RAAD 2025. Enjoy the conference. So I invite my colleague Mirko Rakovic to start with announcing the first plenary talk.
Dear Costa, thank you for that wonderful introduction that we got. So it is my distinct pleasure to open our series of 3 exceptional plenary speakers. Today, on the first day of RAAD 2025, we are honored to welcome Dr. Arash Ajoudani. Dr. Ajoudani is the director of the Human-Robot Interface and Interaction Laboratory at the Italian Institute of Technology in Genoa. His groundbreaking work is evident in his roles as principal investigator for the Real Move project granted by European Research Council in 2023 and the 2019 European Research Council grant Alin. He also coordinates the Horizon 2020 project Sofia, co-coordinates the Horizon 2020 project Concert, and he's the principal investigator for the Horizon Maria Skłodowska-Curie program RAICAM. Dr. Ajoudani's significant contribution to the field have been widely recognized. He's a recipient of the IEEE Robotics and Automation Society Early Career Award in 2021, and also a recipient of Amazon Research Award in 2019, among many others. The title of today's talk is The AI Continuum, from Human Monitoring to Autonomous Robots in Contact-Rich Applications. Dear Arash, without any further delays, we are all eager to hear more details about your work.
Thank you very much. Thank you, Mirko. Thank you, Costa. And it's a big honor and pleasure for me to be here, and the double honor also to start the scientific, let's say, talks today. So the title of the talk is The Physical AI Continuum, from Human Monitoring to Autonomous Robots. So I'm going to talk a little bit about what I do mean by Physical AI Continuum. So just a little bit of, this foreground objective that we have and foreground thoughts we have about intelligent robots, right? From the intelligent robots of today, we expect more when they enter in different applications, and especially in our society, in healthcare and in industry or any other context, right? We want them to not only to basically adapt, but to do more, understand, anticipate, adapt, and collaborate, right? There's a lot of aspects to that. And in my team, we are following 3 principles for that. The first principle is that intelligence must flow continuously, contextually, and consciously. It means that it should be continuous, goal-driven, and and conscious to understand, to perceive all the environment and react accordingly. The second important, let's say, principle that I'm going to build my presentation today is that the physical AI must grow with us, so it should be aware of us. There's no AI that should not be aware of humans, especially in healthcare and industrial sectors, that they're all human-centric, right? So they should perceive and react to different states of the people. And very most important vertical, let's say, line of thought about robotics is the awareness across every point of interaction. So it should not be only against environment, spatial AI, which means that avoiding collisions, avoiding people and stuff like that, but it should be looking into social, cognitive, physical, and all different aspects of the AI. I'm going to tell you a little bit about more. So this brings to physical AI continuum that I'm going to tell about what we are doing from human monitoring all the way to human-robot interaction and autonomous intelligence systems. Let me give you some examples of the human monitoring. So human monitoring is a very complex problem, right? So you have physical factors, cognitive factors, identification of the person for, let's say, for personalization aspects, and their interconnection between all these aspects. So the ground, let's say, tools to be able to achieve those are the kinematics of the body. So today's methods to measure kinematics of the body have really difficulties, long setup times, super costly, let's say, means of achieving those. But AI can help you a lot, right? We are looking into markerless tracking of human body measures. So you're aware of a lot of tools that you can use with cameras with minimum setup times to be able to track people. So we built on top of that, we built a system called Real Move. You can set up the number of cameras that you want in the environment with a very short setup and calibration time of maximum 6-7 minutes, and the system is ready to go. So you can measure precisely 3D kinematics of people entering the scene. We are not using open pose, media pipe, or anything. Everything you see here belongs to us. So with only 4 cameras here, you can see that we are measuring, we are tracking 5 people, and not only that, we are also able to track objects of interest. You see how real-time and reactive the system is, and it's the ground foundation for human monitoring. So Real Move received a lot of funding from European Commission and some national funding, but it's about to kick off as a startup. At this particular point, we are looking into big investors to be able to bring all these technologies, especially their verticals, that I'm going to tell you about it. So we are working on this a lot to bring this into different contexts of human monitoring, right? Identity is one of the most important aspects to be able to provide personalized behaviors for the robots. So in one of the recent works we did, we are able to identify people on the left and the right side. So there's this task of the algorithm to tell me whenever target 1 and target 2 enters the scene. You can see how nicely we are able to identify people at the scene, even if their outfit really look alike, right? Outfits look alike. So on the left and right side, you see when the 2 targets get in, even they're doing different movements, they keep changing the outfits. Through this continuous goal-driven AI that I was mentioning to you, you're able to adapt and always understand who's my target. So this is really important. You want to know who the nurse is, who the patient is, who your coworker is, and all that. And how you do that, of course, we are looking into first trying to do through multi-object tracking. We found and track the person. We go towards detection. We extract features, and all the way to through different computations to understand who's the target. If you're interested, I'm going to skip a lot of math, but if you're interested in any of these particular works, I'm more than happy to discuss it in the following couple of days. The next important really step is to understand the physical aspects of the people, right? When it comes down to physical ergonomics. So we did a lot of work in this over the past 10 years, but I'm going to try to kind of summarize part of this 10 years research in just one slide. So we started looking into dynamics of interaction, no machine learning here, because you don't need machine learning here. Everything, as we were discussing before, mathematically is known. So we were looking into how interaction forces, we used the humanoid theory, humanoid robot theory, because it's real-time, online, and it's really efficient. Using these tools, we were able to build a digital physical twin model of a person through really short, let's say, identification. You ask a person under the cameras to be developed, or with a force plate, or with a variable sensor, whatever you have, to put the person there, and it builds immediately, once and for all, physical model of the person. So here, Luca, just to showcase to you, you will see that he's going to pick this 7-8 kilogram object with 2 hands, and you will see that the circles that are green, which shows the overloading joint torque of the people, how they are changing depending on the loading condition. It means that this is an ergonomic or non-ergonomic, let's say, condition for that person to be able to do. This is real time. So in real time, and in an online manner, we are able to see how the loading changes. Some references here, actually some co-authored with Luca Peternelli, sitting back there when we were working together. So then we said, okay, now we need some AI because we can't really understand where the point of interaction between the person and the environment is, right? So then we started looking into, by building on the theory of, can you see the slides from there? Should I step back a little bit? So by building on the theory of torque equilibrium, we started looking into if we can understand and anticipate the contact point. And when you have the contact point, you can easily build on top of the, let me show it again. So this purple line is the anticipation of where the contact point is. We don't really know where the load is. Everything happens on the fly. And when you understand the contact point is, you can build and tell where the forces and torques are on the body. Then we looked into the compressive forces, not only the torques, but also the forces that go across your body, like push against your, let's say, joints become really important. So we looked into these. In some postures, we showed that compressive forces for physical aspects are way more important than the torques. So our method was based on humanoids. And as you know, humanoids are mostly based on rigid body link dynamics, right? But the spinal cord of the person is way more complicated than that. And then we said, how do we do it? We start looking into spinal cord models, 72 degrees of freedom, whatever models that they have. They said, no, this is an over computation for a robotics person. When we started looking into flexible robots, we modeled the spinal cord like a flexible link. We identified its parameters, and we are able to tell how the torques and compressive forces are propagating against this flexible link. Again, online and really nice tools to be able to use it for identification of the person. So this is some part of the physical aspects that we were doing. We said, okay, one day I was talking to the guys that, when you will see, when robots become autonomous, most of the physical task will be taken over by them. I think the next problem in our societies will be cognitive load, because we are surrounded by smart systems, the systems that outsmart us, and our problem will be a lot of pressure on our cognition, on our mental load. So we really need to build measures to be able to understand how these mental loads are changing. So in industry, we have 2 different ways of understanding mental load. When it becomes easy, we have questionnaires that are extremely biased and hard to anticipate. And in lab settings, we have very fancy systems like heart rate variability, galvanic skin response, and EEGs and stuff like that are really difficult to be deployed in industry, right? We want to be here in the space of deployability accuracy, that you're deployable, easy to use, and you're accurate as close as possible to, let's say, biological systems. So when I look at your faces and you look at your body language, I can tell a lot about your cognitive load and how it reveals itself if you touch your face a lot, if you have some hyperactivity, if you move differently from the way you move usually. If I capture these, I can tell how your cognitive load is changing. So we built an algorithm by looking at nail biting, hyperactivity, and so many other factors, by looking into body tracking measures, and by putting all of that, using AI techniques that I explained to you, like measuring face touching, looking at attention changes, looking at whole body hyperactivity, looking at different measures of, let's say, how the body moves, and putting together, and so after one calibration, only through one camera, you can tell how the mental effort and stress level of a person is. We cross-validated this with some biological signals, obviously, and they match really well. This is not a motor control study. This is something that you want to put in your applications, and it works, right? So next to your robot that I will tell some of those videos. So very non-invasive, very adaptive. You had the camera already. You used it for kinematics tracking, for identification, and you can use it for cognitive load tracking. And before going towards robotics, I want to tell you how else we are using these applications, how else we are using these really nice tools to be able to bring them into good applications. One that we recently published in Roman is for fall prevention. Not only for fall prevention, but also the anticipation of how the person is going to fall. So through some transformers, we are able to, let me go back, to tell if the person is falling and how exactly the person is falling. At the bottom, you see the box there. And after the box, you see the actual posture of the person. At the bottom, you see how we anticipate a person will fall for the next 500 milliseconds through the history of data. So we can tell exactly how the person will fall in such a dynamic, unexpected task, right? It's not like a cyclic locomotion or something that you can really build a model. But our system can exactly tell how this is going to fall. We built models about not only telling the person is alert or not while driving, but also to tell if there are some pathological conditions like stroke, like some heart issues and stuff like that. So try to detect anomalies in different lighting conditions using infrared cameras, using normal cameras and everything like that. So you have these tools, you have personalizable cognitive load tools, tracking tools, you can build all of them to deal with these applications. Something I want to tell, you're among the first time seeing this. It's quite exciting results. Also, we said, so cameras come with a little bit of privacy issues. So if you want to tell if your grandmother has fallen in the house, should you really install a camera? So we used Wi-Fi signals to be able to do that. Home Wi-Fi signals that look like this. So if you're walking in front of the camera and the camera is tracking you, Wi-Fi signals amplitude and phase change like this. So using transformers and AI models, you're able to anticipate only using Wi-Fi signals how the body movements of the person is. You can track the person's key points in two-dimensional at this point very precisely. Let me show you more. In the green background, you see how we're tracking people with cameras. Dark background is how we track people's movements only using Wi-Fi signals. So this is really cool. It's really real-time, reliable, and very, very accurate if you compare it to the visual cameras. So you after some learning, when you pass it through our algorithms using only home Wi-Fi, you can tell not only that, but also some identification of the let's say classification of the actions. So here, Yangel, my postdoc, is Wi-Fi signal tracks and says you're walking through some identification. What really cool is that on the right side, you see we are able to tell how the person is doing, and eventually we are simulating falls, and you will see how we are able to tell if the person has fallen. Again, only using Wi-Fi signal. So this is a groundbreaking result, right? Using only Wi-Fi, you can tell what's happening in the home of an elderly person. For instance, if there has been an inactivity for a long time, you can tell. So this is key to improving healthcare for people in their homes. Now go a little bit about robotics, just shift a little bit about robotics until we go about hardcore robotics at the end. So in general, we work with mobile robots. My PhD thesis, part of it was on humanoid robots, but in my lab, we don't really do humanoid robots for many reasons. Especially our applications focus on healthcare and industrial environments, which 96% of those environments are flat. You don't really need leg locomotion. And these are, I don't want to go through them, but there are many reasons why we are using mobile manipulators. They are mechanical simplicity. You don't have to worry about legs and stability and stuff. Energy efficiency. You can stay there without using energy, because in leg robots you have to always make sure that you're consuming energy to make the robot stable, even if you're standing and doing nothing. But with a base like that, you don't do anything, right? They are relatively lower cost. I'm not sure about that anymore, because now with humanoids of R1 and stuff at 20,000 euros, probably they are going a bit of interruptions there. And a lot of good technical specifications that, for instance, payload. We're talking about humanoid robots, but most of these humanoid robots don't have a payload more than 3 kilograms. They're good for, cognitive tasks, but you can't really expect them to do industrial tasks that KUKA, FANUC, and these kind of stuff do. Even the collaborative robots that go about 16, 17 kilograms of payload. So now let me tell you how we are bringing these robots and the tools I showed you in the past to be able to create a smooth, intuitive human-robot collaboration. In this particular task, through the human tracking and identification that I showed in the beginning, the robot's task is to follow the target person. The target person is the one that is in the blue shirt, and that we ask the robot, do not get confused, only follow him. It's in the environment, it's in the hospital, it can be anything, a doctor, or in an industrial setting that is just grab a tool and follow me. You see, there are some parts of it. Let me go to the next video, which is nicer. You will see the same thing. We also said how we can actually build an intuitive communication and stuff like that. LLMs are really good, but language in industrial environments are not very welcome because there's already a lot of noise. So if you don't want to add noise to those environments, you should really rely on more other intuitive means of application. Language is good in healthcare, in home services and stuff. By language, I mean speech. But you know, in simple tasks like gestures and stuff like that can be really useful. So building these two together, gestures, identification, and you will see how the robot is able not only to follow the exact person and follow the commands the person is giving, very simple, just stop, follow, and stuff like that, but also is able to avoid static, and dynamic obstacles. So here, Andrea is just moving around and giving some comments. You see people are just walking in front of the robot. The robot is safely avoiding them and focuses on the right person. Here we intentionally avoided the robot, and then as you can see, we have built a feature that the robot actually looks around, looks at each, remember in the fourth slide I was showing how you need personalization, finds the right person, says, you're my guy, I'm gonna stalk on you. If you ever feel lonely, we can send one of these robots to follow you anywhere, and then all of a sudden you have a friend. So again, sampling a little bit about, I really don't know what your backgrounds are, so I'm sampling a little bit things that might be interested to most of the people listening to this talk. Looking into physically interactive tasks, right? So when we talk about human-robot co-carrying, which is when you talk about human-robot collaboration, if you have worked on it, one of the tasks that comes to your mind is that co-carrying is one of it. Although there's not many relevance in industry, but it's a very complicated problem. You see this one at the bottom left, it's non-rigid. It means that you can't really transfer forces from the leader to the follower. And I can move my arm and the robot won't feel any forces and it won't respond. In fact, in most of the co-carrying works in robotics are based on forces, based on admittance control. The intention is estimated through the forces you're applying. So that thing never works there. When it's rigid, then yes, you can follow the forces and this definitely works. Just to, what did I do? Okay. So this is exactly what I was telling. So if you work on haptics-based and make the robot move through only forces, you have really nice behaviors. But can you use the same thing with a rope? No, because you have no or absolutely partial reflection of the forces felt by the robot. So we said, now let's blend information that we have from vision to make sure that the rope things work. You just look at people moving, we do the same. You're moving and I'm moving because there are no forces. But how do I do with the haptic space? Because it's rigidly coupled. In order to be able to move, so I have some physical constraints. So what is the answer? To blend, to merge these two information. So we did that. Let me skip. So this is an adaptive controller, looks at the movements, looks at forces and merges all together and creates these really adaptive and nice behaviors. That's a partially deformable object that you can see the robot is able to carry. This is the rotational element, so we are looking at the body language through the kinematic measures that we were saying. If you give the intention, we are able to estimate the intention, and the robot is able to do that. So this you saw was a former PhD student under a lot of pressure, couldn't make it. I'm kidding. So you can see how nicely we are able to carry with and without, the essential reflection of the forces. So we are looking at the twist and wrench, everything reflected on the robot side and give the adaptive behaviors. Then we said, maybe we need more robots, right? Maybe the object is bulky and big. Maybe we have these scenarios. We extended it in another work. We call it adaptive control interface. By looking into that, we are able also to achieve that. On the top left, you see it's a rigid box, and the coordination between the robots are very intuitive. On the bottom, this is a nightmare for robotics, right? Because you have ungraspable box, robot coordination, the rope is flexible, so everything bad for robotics is there. But through this algorithm, you're able to perform it. So you project everything on the robot, and then through some simplifications, algorithms that we have, you're able to co-carry such a nightmarish object, right? So going up and down an intention is easily estimated and sent to the robot. So when it comes to the physical let's say, factors that I was explaining to you, this is the physical behavior, the physical model of the human that you saw in the first slides. This work goes back a few years when we won the KUKA Innovation Award, and you can see how robot is adapting to the physical parameters of the person. Many of you are familiar with this work, but what happens is that if you're working with a robot and the robot sees there's loading on your shoulder, for instance, it changes the configuration of the task and brings you to a configuration that the loading is less. And when you're moving in the environment, the robot adapts to your movement. When you're switching hands, the robot adapts to the movements of the switching hand and stuff like that. And everything is done through a camera. We showcased it in 2018 or 19 in KUKA Innovation. And we won the award. And after that, there was my ERC grant on this. And we worked a lot on adaptation of the robots. There's a lot of works in this. If you're interested, I can send you some papers. But again, sampling, I was mentioning one of the biggest issues is how we can make robots adapt to the human cognition. So in this particular case, what we said, let's make the robot's behavior matching and adapting to the level of cognitive load of the person. So making sure that the person has the right amount of engagement, not too low, not too high. If it's too low, it means that the person is going to get bored. If it's too much, it brings anxiety, overburden, and all that. So this algorithm is quite sophisticated. It looks into different measures of, let's say, cognitive load and goes through a Pareto front optimization. Here, you want to optimize between productivity, which you want to be as fast as possible, and cognitive load. So basically, and then you adjust it based on the level of cognitive load of the person that you have. The video is very self-explanatory. So Marta is working with this robot, and the robot starts very slowly, understands rest, so the person is not engaged enough. The cognitive level of engagement is not good enough. Then it starts pushing on the jerk, so pushes on the productivity, which means that the acceleration of the robot increases, the velocity of the robot increases, until it detects some stress, because the person lags behind, and the robots, you see in this Pareto front optimization, adaptively switches back one step. So it optimizes for that level of stress that day you have. So we have different cognitive capacity, and this cognitive capacity every day changes. You might have had a fight with your partner, you might have had maybe a couple of beers the night before, or things change, and you have to continuously, consciously, and contextually adapt. This is exactly what we were mentioning, so continuously adapting to the states of the person. Then we said, okay, now let's build a little bit more on that. So who's familiar with the traditional safety limits of industrial robots? So ISO standards are making our life really difficult, because ISO standards are based on inertia, acceleration of the robot, and then you're saying if the robot is big, it's not collaborative, and it has this inertia, you cannot go beyond this level of acceleration. It means that in our environment, it means that if a strong guy comes from that door, he's a big bodybuilder, comes from that door, and you're saying, oh, I'm not going to work with you because you're strong, you might hurt me. Nobody says that, because we're relying on the intelligence of that guy to be able to avoid collisions with us, right? So we want to do that. Not necessarily every strong robot can hurt you if you have the right tools. So we are adjusting these boundaries. And one of the tools we are using, let me avoid that, is based on the attention of the person towards the robot. So if you're looking at the robot and the robot is moving, it means that you have a larger reaction time. Something goes wrong, you have a larger reaction time to avoid. That's why we are avoiding, we are shrinking the safety limit. That's why you see that the robot is going closer to the person. Not too close, we have this red area you can't enter, but you see the robot is making that path. But in the second trial, the person is not looking at the robot. So by not looking, it means that your reaction time gets larger. You need larger time if something goes wrong to save yourself. So the robot trajectory becomes more conservative. It means that it gets way more far from your side, right? So this is really cool because depending really on the level of attention of the person, you can scale the safety of the robot, a safety level. And you might say, so what's wrong in being overly conservative? It's awkward because the robots stop when you're moving, and then it's unproductive. That's why you don't see many collaborative robots in true means of collaboration in industrial applications, because they have to move so slowly in front of people. But with these tools, we are able to push the boundaries, right? Then, of course, we had safety constraints and cognitive load. We said, let's put everything together. So now in this particular work, both the trajectories are optimized based on the attention of the person, and the velocity of the robot is changing based on the cognitive load of the person. So every aspects are integrated into one. You can imagine what happens. I'm not going to stay longer on this. I don't have the time. How much I've been speaking? I have 10 minutes? Okay, I got to go a little bit faster. So back to this beautiful slide, but this time for trust. In human-robot interaction, you see here a lot about trust and explainability and stuff like that we heard this morning. So trust in human-robot interaction, again, there are questionnaires. We love and hate questionnaires. Questionnaires are easy, and then you can write the questions the way your paper wants it to be. You write the questions in a way that you always win. But then we have eye tracking, HRV, and GSR to understand the trust of the people, right? This is difficult. This probably won't work in today's industry. Again, we want to be there. So for the first time, we built a closed-loop optimization procedure based on machine learning to improve trust of people in human-robot interaction. And how it works. Do you have a mic that I can even walk? No. Is it detachable? Oh, super. So this works like this. In your application, you have some parameters, right? You have some parameters. This is a very simple chemical application. These parameters are the distance, for instance, of target to the pouring. It was a simple pouring task. The distance of the robot that should fly, the smallest distance you let the robot come close to you, and the height that the robot should pour. Simple. You pick 3. And then you build a preference-based optimization. It's a reinforcement learning algorithm that you put these values, these parameters into the optimization, and through interaction with the person, you optimize them and you converge towards the best parameters that improves the trust of the people. So this is the video. You start from some random parameters of choice, and you always ask the person one question. Do you prefer this behavior or the behavior that I gave you the previous interaction? You just need to say this one or the previous one. It builds the optimization. It's a very sophisticated and beautiful algorithm that converges all these parameters towards a locally optimum, obviously, but optimum choice of parameters. It can be damping, it can be stiffness, it can be any parameter of choice. What is really exciting is that on a large number of subjects, after a few iterations, about 16 iterations, the parameter of choice matches the exact parameter that you ask them to be. The height matches the thing without really explicitly asking them what height, which distance, what this, what that. The algorithm optimizes just through one thing, yes or no. Because you can't go to a nurse and say, what level of stiffness you want from this robot. They won't understand. You just say, you like it more or less. Less, more, and you arrive to that. And this contributes to better trust. This we published very recently, and this is probably one of the first closed-loop ways of improving trust and personalization of the systems. So far, I talked about physical ergonomics and cognitive ergonomics separately, and one of the questions we had is how we can bring all this together. So in psychology, there is a concept called coefficiency, which means that when I work with Boyan, for instance, we are coefficient. If he asks me, can you pass me a coffee? I don't pass him all the way through him, so he's very comfortable. I pass him somewhere in the middle that I am comfortable, he's comfortable, everybody's happy. So this coefficiency makes the behaviors look very natural. We brought this concept into reinforcement learning, which means that I have several things that I have to take care of. Robotics, productivity, cycle times, whatever you want to call it, cognitive ergonomics, and physical ergonomics. We put it in a reinforcement learning problem, define the costs of choice, and we asked through interaction, can you optimize all this for me through an iterative process, another iterative process, and this turns out really well. So this is the first time you can see that how cognitive, physical, and robot parameters all come together. The task was simple because we wanted to isolate the dynamics of the task, so make the focus, put the focus on the algorithm. And we didn't even talk about the parameters of choice this time, right? So we only optimized for physical ergonomics, range of movements, fatigue, and everything. Cognitive ergonomics, how much attention the person should, so you really need to look at all the time, or you can relax because the robot is becoming intelligent. And the productivity, for the robot case here, we just looked at the thermal cost, the amount of torque, fatigue of the robot, how much torque the robot is applying. So through all this, the algorithm, it goes, but really nicely it optimizes all the parameters. On the theory side, we optimize all the parameters, but the side really nice effect was, again, all the let's say, behavior of the robot matches the preference of the person. So this comes this time as a side thing. So in the last part of my presentation, I want to talk about only autonomous robots. So here we don't want to have people because unstructured environments, repetitive tasks, and things like that. And here machine learning can help a lot. Machine learning in robotics have a lot of, let's say, ways of implementation. So these are some, not limited to, but we are working on almost all of these, but I'm going to highlight a few that are the most recent. Learning from human demonstrations, everybody knows about that, right? So to be able to learn from human demonstrations in mobile robots, we built this interface. This is called Superman. It's called supernumerary bodies for human-robot co-joint actions. What is really cool about that is just by attaching this to your robot, you can switch between the mobility of the base and the arm. You don't have to wear anything. You can transmit forces. You can transmit, let's say, anything you want. And it turns out to be actually really useful. So you can do a lot of tasks that you need exoskeletons or other stuff for that, but this can be replacing some of the tools that you can have. Over-the-shoulder drilling in automotive industry is really difficult, so we were managed to do that. The payload is 16 kilograms, and you're feeling 5 newtons max to be able to do something like that, right? But coming back to the learning, we try to use this system to encode the behavior of the system. So from this interface, what we can do, so there's a force torque sensor here, and a robot has a force torque sensor here. So we are isolating the intention from interaction. This is a must. It's not easy to do that only with one force torque sensor. From here, you have an admittance controller that gives you the desired velocity and position of the robot. This interface indirectly helps you to learn stiffness behavior of the person. You can't do that if you want to learn the stiffness behavior. I mean, people have been working on this. My entire PhD was on that through biological models and other types of models and stuff like that. It's not easy. But so we try to detour this problem by looking into, you show me your behavior, I'm gonna measure and learn through machine learning the trajectories and forces. Then I'm gonna replicate it, the same behavior in the robot, the trajectories, but with the stiffness. Now let me ask you one question, especially the PhD students. Why force control, pure force control is bad? So why don't you just measure the forces and trajectories and just replicate the forces and trajectories? Why don't you do force control? Anyone? Why force control is bad in industrial applications? Seniors? You look like Boyan. Yeah. Not only stability, but it's dangerous. Force control, if you have 5 newtons, if you're asking the robot to give you 5 newton, if you lose contact, you really don't know what's going to happen to the robot because the robot is going to go until it finds that 5 newton. In robotics, especially when it comes to human-robot interaction, you always need to know where the robot will stop. But in force control, you will not know where the robot will stop. So if I'm asking the robot, give me 10 Newton, 10 Newton, 10 Newton, I'm cleaning, I lost contact, and it accelerates your robot, it goes until it finds the 10 Newton. And if that point is your arm, your eye, your head, you know what happens. So it's bad. But impedance control gives you indirectly the right force response, but it's stable, and you know where you're stopping. You can always manage that. So this is really cool. So this is the application of machine learning plus passivity-based control, which makes our robots good. So I don't want to go to the details, but what we do, we are minimizing the tracking of the force, but we want to be as close as to the minimum stiffness because we want to be as compliant as possible. Compliance means safety. So give me the minimum stiffness is required to be able to track that force. Since you're changing stiffness, people know that change of stiffness modulates the energy of the system. You might store energy more than you dissipate, so you have to observe it. We have the energy tank optimization that looks into how much, if the system is passive, and then you do all the cool stuff. But the video is nicer. So you do demonstrations. This beautiful interface gives you the ability to use the base, so you have a larger demonstration space, so you can actually teach base movements. This can be a humanoid robot. I don't hate them. It's just saying that it's easier to use. This can be a humanoid robot. So you're teaching this interface. You're taking and you're learning the forces, learning the trajectories, but then you're replicating them autonomously using impedance behavior. So this is in nominal condition. This is under severe disturbances, and the robot is able to give you the best force behavior. You see how this doesn't detach. It keeps pushing. But when it loses the contact, you know where the robot will stop. So this is really cool, right? This nominal condition force tracking is perfect. Even with the really severe disturbances, the robot is able to give you the best behavior. Sampling from the things, learning from offline human videos. This is something that's very new we are working on. This is a recent transactional robotics paper. We brought the information theory, which tells how components in interaction talk to each other and how the flow of information is. We applied to the perception by looking at the components from just offline videos. We used Aruko markers, but you can use SAM, segment, anything, any particular tool you like, and automatically you build the interaction between the components. Objects and objects, left-hand, right-hand objects, and you build it in your scene perception. So, human understanding, information theory, scene perception, and then automatically you build your behavior tree. When you build your behavior tree, the robot can execute it autonomously. Some offline videos directly gives you the robot code. You just show an offline video with the level of perception that you want, and the robot can replicate it. Why is better than the black box that was mentioned before? Because it's modular. Explainable because you know what's going to happen, and behavior trees are like state machines. You can add and remove whatever element you want. So here we are showing that if you add objects, remove objects, change objects, the system will adapt because it's a behavior tree. You can change it. Then we extended it to the dual arm system. These are all new stuff, T-Row, and this was just a few weeks ago published in RAAD. We extended the dual arm applications just to show we are able, by using this very powerful tool of Shannon's information theory, by looking at the mutual information and everything, to tell if the behavior is synchronous, asynchronous, and behavior tree is generated through sequential and parallel tasks. Doesn't matter if it's symmetric, asymmetric, and everything. And the robot is I don't know what's going on. Robot is able to execute it. Just a few slides left. My presentation went unstable. I think I wasn't looking into the energy entropy. It doesn't work. Uh-oh. In one presentation, somebody said, Microsoft did the best job of not working on making it robust, but they worked a lot on making the restart faster. So if you restart a computer, we can't solve this hanging problem, but we can make the restart faster. So it's going to take just a few seconds until it reboots. My name is Arash Ajoudani. I'm the Plenary speaker. No, kidding. So then what's next? The big hype was video demonstration. So where's me? Where's my input in there? And what comes is the context awareness of large language models. Large language models, thank you very much. Large language models are not only for speech. They have an amazing context awareness and rationalization capacity. So what we did, we brought large language models to talk to our behavior tree. So far I presented this, scene perception, dual arm, one arm, whatever, behavior tree creation, and what if I want to change something? So you can ask the person. Then we added this conversation to the naive user. So what happens here is that there's some audio, but it's not required. Again, you show some task and the robot learns to do it. It learns the target points and stuff like that. But this is the replication, right? So the robot picks this. This is the behavior tree created autonomously. The person shouldn't know this because the person, I don't even know if he's a PhD in robotics. And this happens. So what do you expect from a person to say? Increase the height, lower the stiffness, I don't know, this and that, and use intuitive words. You know, pay attention, do not collide. And in the second interaction we said, pour less water. Pour less water. So initially, the behavior tree, sorry if I want to show you something. So behavior tree, LLM intervenes the behavior tree and it changes on the fly. So pour less water, before it was 90 degrees. LLM says, if 90 degrees is too much, maybe 45, 60 degrees is good. So it's tilting 60 degrees. Everything is happening automatically without it. It's just the person said, pour less water. But LLM's contextual awareness says, when inclining 90 degrees too much, 60 degrees should be good. And when arriving collision, maybe that height is not good, I should increase the height. So it arrives there 60 degrees and doesn't collide. You see how powerful it is, LLM? It's not only for speech, but also the rationalization behavior of the system. This is an IJRR, no, it's a RAAD paper. It's accepted actually. This will be published in a few weeks probably. So we put this together and we are really happy with that. Just a few minutes I'm finishing up. Something that we really like is not even to ask humans, but it not always works. So something that we want is robots to learn by themselves. This particular task is a very difficult, non-prehensile problem of putting this object in the middle of the surface. And the robot builds accelerations and everything is able to do that. And why it is challenging? Because the friction is not always known. In this particular case, the robot knows the friction and it's able to slide. It's not an easy task for a person. Even if you do it 1,000,000 times, you can't do it. But the robot can easily do it. You saw in this video. You see in different configurations. But what if the friction is not known? The learning system can tell you, if the friction is not known, I would understand, and I can have the second behavior to match the system. So this is one machine learning algorithm that uses an analytical model, but this is a machine learning algorithm that uses an LSTM model to anticipate. Friction was wrong, second stroke, everything good. So this is also a RAAD paper just published. We are able to learn, they are able to learn by themselves. Obviously, a lot of this can be done in simulations. You learn your simulation model, you bring it to the real environment, and you do it. We were talking about grasping, something that, this is an IJRR paper just published, but this is not about learning, this is about control. Grasping problem in DLR, we had a lot of beautiful videos, but something that hasn't been looked into is, if I throw you a watermelon, how would you catch it? You won't go against it. You accompany it and you grasp it because you want to minimize the impact. There's a lot of stuff happening there. You're minimizing your impedance because you want to avoid the bouncing, you dissipate the energy, and you avoid the impact through the velocity matching. So these are really cool behaviors, right? If you're interested in the optimization and control part of the problem, please read this paper, IJRR. You see this accompanying issue that this robot is doing, we call it velocity matching, and the stiffness changes that damps the energy. And we said, can we learn that? This hasn't been published. This is purely ongoing work. I don't know why it's showing like that. But we are trying to see if the robots, without telling them to do these behaviors, they can learn by themselves, because you can tell them, reduce the impact, anticipate the energy. And we are getting there. It's very close. Adaptation through interaction. This is also some new work recently published. Who knows about actor-critic reinforcement learning? Yeah? Okay, super. So I'm going to explain just in 10 seconds. For the first time, we brought actor-critic reinforcement learning and variable impedance control. So what it happens is that if you have contact-rich manipulation tasks, The safety critic learned offline tells you if there's a risk in contact, and the risk means what? High interaction forces. If there's yes, you train your recovery policy to reduce those and to mitigate that risk. If no, you use task policy. This has been learned, the offline part, which is read offline, and the online part keeps learning that. So safety critic neural network is reinforcement learning is really good because it's the best for what if something goes wrong. So you learn that. And obviously on top of that, a variable impedance control changes the impedance of behavior of the system in contact recapitulations. We tested it in maze following application. So here the robot does not see the maze. We said, change the impedance in Boyan and I think in JSI, we worked a lot on this, Change the stiffness just in a way that you're able to pass, change the stiffness ellipsoid just in a way to pass through the maze. You can see the stiffness ellipsoid changes. It learns how to change when it comes to obstacles and stuff like that. And when the interaction forces go high, safety critic network says, the critic network says interaction forces are too high and gives the input to the critic network and says, I can change the stiffness and the velocity of the end effector to make sure that this doesn't happen. And you can see all these really nice behaviors change. Going super fast. Again, this is some purely control-based problem. We wanted to do non-parent manipulation just using the base to push the object. This is a force sensor that we use to push, non-parent manipulation because not every collaborative robot can carry more than 10-15 kilograms. This is 25 kilograms, and we built a really nice reactive strategy. For this, you don't need machine learning. This is really cool. Let me avoid the math, but let me just show you super nice results. Any type of objects we put, it was able to push. It was sensing. It was sensing through the skin that it's our own. And you see how nicely it can go. It push the object. You put a cylinder of 25 kilogram. It changes. It's very reactive, nothing pre-planned. It can take to the final goal. And the very last one, you see, very different shape, and also to show you the reactiveness. Ideal, my PhD student is just playing with the robot, is pushing the object here and there, but the robot is able to react and always give the right behavior. Nothing about machine learning here. Why? We don't need that. Through some really cool behaviors, you can achieve that. But what's relevant to machine learning? Because you might say, I neither have the money or energy to build the skin. Tactile skin to do this. And my mobile base, I just bought it. I saw one actually from Robotics. I don't have my tactile skin. Can I use your controller? Yes. So we brought the concept of sensory substitution, which means that I can learn my behaviors through another sensory system to learn the association between that sensory system and the tactile sensing. So if you have an RGBD camera or a LiDAR sensor, this is the work we just, it's an archive, but we just submitted it. So through that, you can learn the contact behavior of the tactile sensor through vision, and you substitute in your controller with this. So the LiDAR RGB camera acts like a force torque, like a skin. And this works even better. You know why? Because with the perception, you have the anticipation. You see the object is coming. But with the force, you need the contact to be able to see. So these are basically with LiDAR and with the camera. And obviously, we did this on many things. There's no skin sensor here. You can see all different objects and different shapes. The robot is able to push objects that you can't grasp with one robot, right? So it can be post-disaster response, to be able to move the obstacles away from the scene and stuff like that. And obviously, there's one part. You can see Doganai here is kicking the box, but the robot is able to do that. Finishing up, so happy with the results. Machine learning, everything is good. They are smart, yes, but none of these applications I showed you are safe. Safe in a sense of safety actor-critic network, but from control theory point of view, none of these applications are safe because you don't really know what happens in terms of energy in the system. And these are some stupid questions. Of course, the answer is no. Would you partner with a robot that fails 1 out of 5 times, and I will tell you what. So if you're using reinforcement learning and the only thing you care is about task performance, you might learn to achieve that through high-frequency vibrations or unbounded energy accumulation when it comes to contact, when it comes to stiffness regulations. And these things in real applications can make your system unstable. And instability is not a joke, especially when you're carrying a sharp object next to a person in an industrial environment, or you're injecting a syringe into a patient. So even this work that I showed you was why we thought about this, but because the task was done perfectly, but we looked into the energy flow of the system. In some cases, the system was not even passive, even if it was successful. So it means that the system had the potential to go unstable. So this is also something we just submitted, and we are bringing the concept of passivity into reinforcement learning. There are different ways of doing that. This is passivity agnostic, which means that what I explained you, actor critic. This is passivity aware. Who's familiar with the energy tanks and stuff like that? Okay. So passivity aware is like you do your RL, and in the last layer you put your passivity observer, energy tank or whatever, and change the behavior. You cut whatever is non-passive. It works, but it's not as good as bringing the energy constraints, the passivity constraint into the learning, but also having the last layer just to make sure that you're not creating unpassive behaviors. And the difference between that is passivity agnostic doesn't know anything about passivity or energy efficiency. Passivity filtered is passive, but it's not energy efficient. But if you make sure that also you bring the energy concept into the learning, you're both passive and also energy efficient, which means that you are using the least possible your energy budget to be able to pursue the task. I'm done. Just a little bit of thoughts for you. I think the future of human-robot interaction should be not only co-adaptation, because co-adaptation means that humans and robots should co-adapt. We don't want that. I usually use this term of co-evolution, which means that it's one step after co-adaptation. I'm adapting in a sense that we both earn something. You know, the bee and the pollination issue. They're adapting to each other, but at the same time, both of them are getting something right, out of this. So if you want to bring this, if you're working on human-robot collaboration or interaction, the way to achieve that is to bring human factors in one circle, bring robot factors in one circle, because at the end of the day, you have to earn money, productivity, cycle times, and anything. And this should be where we should look into. So both systems should bring benefits. I would call it co-evolutionary HRI. Thank you very much for your attention. I hope I didn't pass through time, and I would like to thank my team for this wonderful work, and thanks.
Thank you, Arash. It was an inspiring talk. It fulfilled my expectations. I hope everyone as well. So we have time for 2 minutes. For 2 questions, sorry, and we decided to shift everything for 15 minutes, so we will have enough time for a coffee break. We start with the session at 10:45, okay?
Thank you very much, Arash, for a wonderful presentation. I was particularly interested in this sensor substitution, and my question is, can you do also mixing of sensors to have like a multimodal sensory system, not just a substitution of the sensor? Thank you.
Thanks a lot, Boyan, for the question. I think yes, and there's nothing that comes to my mind that should not be done. Actually, it can build on the robustness of the technique, right? So when you do sensory fusion, you have way more data, and it builds on the, machine learning is based on probability, and then when you have more inputs, the probability of reaction gets higher. Especially with the learning parts in this particular work can improve the anticipation of the robot. We haven't done that yet, but multimodal sensory input for machine learning is a long going discussion, and it's always good. But in this particular case for us was that sensor is really expensive. To our surprise, the tactile sensing, we have been talking into this. I mean, my robotics background goes 15, 20 years, not more than that, but I think our seniors here can tell more. I mean, since day one, we always talked about tactile sensors. And when I came to robotics and I said, I'm going to buy one of these tactile sensors, just equip my system, nobody's selling them. Where are those tactile sensors? Everybody thinks it's a solved problem, but nobody's selling them. And if they are selling, the moment they sold you, they block you from emails. You say, it's not working, there's bias, nobody responds. So we had to build our own. And that's why we said, what if nobody has that? So I think we should get back to this. Thanks for the question.
Thank Thank you. Okay, one more question.
Hi, Ash, and thanks for your presentation.
Of course.
Actually, I also curiosity about the sensory substitution. So I just want to know what's the main purpose of you doing this? If you want to do some finding some cheaper alternative sensors from some modalities, or we merely want to do something safety, like when one sensor is broken, we could find some other new alternatives to rely on. Yeah.
Thanks. So the reason for that was in some systems that you buy, you don't have sensors of choice because they are usually expensive or you can't find them. In our case, as I mentioned, we built our own sensory system. But for other researchers to be able to use our algorithm, they can't do that because they can't really start building. They can, but it's time consuming. So can you use this nice control algorithm on a system that really don't have those sensors that your system has? But can you find the mapping between these? So that's the solution. So you can imagine a humanoid robot that doesn't have a torque sensor, right? How do we estimate contact? We can estimate contact through vision, maybe some impacts, maybe you can see if something is colliding and stuff like that. So if you don't have a sensor, or you have a sensor that its performance is less, through sensory substitution or sensory augmentation, you can combine or replace the inputs. So this particular framework works when you don't have that sensor, right? But if you find and replace, you find and replace. So now what we are working on is this. You have an algorithm, like our algorithm. My machine, my controller is completely different. My sensor system is completely different. You build a simulation that learns not only the controller, but also the sensory system. So you build the transformer or anything that you want that replicates the same behavior of the system, learning from control and learning from sensors on a different sensory unit. So this is amazing. This is the best copy-paste. This is copy-paste in robotics without knowing anything about what's going on inside the heart of the robot, right? This is what we do with humans. We just, like robots doing backflipping in reinforcement learning. You put the kinematics, right? You learn the kinematics, you put it in a robot, you say, do 1,000,000 times, 1,000,000,000 times until you figure out not to fall. You don't know what dynamics, those things we did in DLR, in the IIT, in CNRS, they did optimal control, but it's super difficult. But these techniques, this is where machine learning thrives. Thanks.
Okay, thank you, Arash. Arash will be here, so approach him to ask. Arash, we do have present.
Oh, thank you very much.
And the present for you.
Oh, that's amazing.
Coffee time.
I really appreciate it. It's hot in front of the screen.
Yeah. This is why I left the jacket.